Here's the solution to problem number 5. So a cube of wood, density 780 kilograms per meter cubed, is 10 centimeters on each side. When placed in water, what height will the block float above the surface? The density of water is 1,000 kilograms per cubic meter, which is something you should actually know. Alright, so here's the wood, and I've kind of colored in already the part that's below the water line. Remember, when figuring out the buoyant force to hold it up, it's always the part that's under the water, not the whole block of wood. That's what I need to figure out. So what I want to know for the buoyant force is this: the area that's underwater, and specifically the height of that little piece of wood. Since I'm talking about the wood floating and I'm talking about the buoyant force, I'm going to have a free body diagram. So what's being held up is just the weight of the block. Nothing else is on top of it. If there were other things on top of it or around it, I would just add them to this force, but it's just the weight of the block. And going upwards, that's going to be counterbalanced by the buoyant force. Since it's not accelerating, all these forces are going to equal 0 when I sum them up. Sum up some forces in the I gotta speak again. I'll sum up the forces in the y direction. That's equal to 0. That's equal to the buoyant force going up minus the weight of the block going down. So 0 is equal to the buoyant force minus the weight of the block. Therefore, the buoyant force is just equal to the weight of the block. So the buoyant force is rho vg. That's rho, the density of the water that it's sitting in, the fluid that it's sitting in, times the volume that's underwater times g equals the weight of the block. This is different than the blimp problem. In the blimp problem, you had the entire blimp was submerged in the air. But this time, my fluid's are water, and only part of the block is submerged. So when I'm looking at the volume there, I'm looking at the volume that's underwater, not the whole block. And that's the difference in the two problems. So I'll expand this out a little bit more to describe the volume in terms of area times distance, and that d is going to actually be the depth of the block. The vertical distance in the area is going to be the 10 centimeters by 10 centimeters. So the weight is equal to the mass of the block times g. And I can see some things happen with the g's, but I'm just going to leave them in there for a little bit. And I'll keep going because I don't have the actual mass of the block, I have the density of it. So because of that, I'm going to find the mass by taking the density of the wood times the volume of the block, the whole block. So buoyancy is just the part that's underwater, and now I'm looking for the mass of the whole block, so I'm taking the volume of the whole block. Alright, so let's keep going. Next step, I'm going to define the volume of the block. That's area times length. Notice I didn't use depth. It's the whole side of it, that 10 centimeters. And I did that because the areas will divide out. So that's what I was going for there. So now I know that the density of the water times the depth, the block is underwater, equals the density of the wood times the length of the side, the whole side length, the whole height of it. Slide this up a little bit. And now I know that the depth of the block that's underwater is equal to the density of the wood times the whole side length of the block divided by the density of the water. So the height that's above the water is equal to the length of the side minus the density. So that's equal to length minus density of the wood times the length divided by the density of the fluid it's in, of the water. Putting in my numbers, doing a little bit of math, and I get the height above the surface as being 0.022 meters.